This conference will now be recorded.
So freezing takes place particularly during low temperature, during winters, and thawing or melting takes place during the hot weather conditions. So when water freezes, its volume increases. Because water, it has maximum density at 4 degrees Celsius. When we go below 4 degrees Celsius, its density starts increasing. Density increases means, sorry, the density starts decreasing. It means the volume is increasing. And this results in expansion. And this is the reason probably that the ice when it is formed, it floats over the surface of water. So freezing increases the volume. Now the water which is present in the pores and cracks of different rocks, when freezes, its volume increases. And that increase in volume exerts pressure over the different layers within a rock. And that exertion of that pressure results in formation of fine cracks, microfractures, and these microfractures keep on widening with time and ultimately result in cracking of the rock, breaking it down into smaller fractions. So freezing and time is related to temperature. Second is heating and cooling, and it is equal to thermal stress. Here water has no role to play. Heating and cooling simply of the rock is a result. Temperature is an important parameter here as well, but here water is not a part of the weathering process. So heating and cooling results in loosening of different layers of the rock, and these layers with time get loose, keep on withering, keep on cracking, keep on firing. The third is wetting and drying. Many times the cycles where the rock material is getting wet once and then getting dried once. So during wetting, some sort of expansion in the structure takes place, and during drying, normally the contraction is observed, and during drying, normally the cracks are formed in the rock, and these cracks result in weathering of the rock. Third is grinding and rubbing, and grinding and rubbing is just because of the action of wind or water. And this is normally the weathering feature of the wind or rivers or glaciers, etc. Unloading also results in cracking rocks. The sudden release of pressure, particularly during, say, landslides, etc. When landslides takes place, the pressure over the underlying rocks is released, and these rocks, when pressure is released, sometimes form cracks, and these cracks keep on widening, and this results in weathering. So these are different processes by which physical weathering takes place. Now, in case of chemical weathering, it is some sort of chemical reaction which is involved in breaking the rock down into smaller fragments, smaller parts, and resulting in soil formation. The first is solubilization or dissolution. In case of solubilization or dissolution, some part of the rock is soluble in water. Suppose we take the case of halite rocks. Halite is NaCl. You must have seen the rock salt being sold in market even. That is the halite rock. And since rock salt is easily soluble in water, the salt is easily soluble in water. Wherever it is present, if water flows over it, dissolution of that part, dissolution of that halite part takes place easily, and that is weathered. And this results in formation of holes at different places. And with the formation of these holes, the rock material gets exposed to external forces, external factors, which further result in weathering rock. And solubilization also results in loosening of different layers of rock. The other type is hydrolysis or hydration. In this case, the molecule of a mineral absorbs water. And absorption of water results in swelling, and swelling results in loosening of different layers. Also, many times, hydrolysis or hydration results in solubilization of some particular molecule in water. And this is a bit different from solubilization or dissolution. Here, in that case, solubilization or dissolution, no change in chemical structure of the mineral takes place. But in case of hydrolysis or hydration, the water is absorbed by the mineral and it gets expanded, then it gets solubilized in water or is washed. Third chemical process is carbonation, where carbonic acid is formed, and carbonic acid is formed by the dissolution of carbon dioxide gas in water. When H2O reacts with CO2, it results in formation of carbonic acid, which is again a weak acid. Now, carbonic acid can result in dissolution of some of the minerals, some of the chemical species which are present in the rock, and this results in removal of certain softer parts, softer minerals present in a rock, and that those are washed down easily. So carbonation is also one reason. If we explain carbonation in more detail, calcium carbonate rocks, Chuna Pathar, most of you must have read about or seen the rock. Calcium carbonate is insoluble in water, but when it is exposed to carbonic acid, H plus reacts with CO3 part of calcium carbonate and forms bicarbonate ions. And these bicarbonate ions are soluble in water, and the remaining calcium hydroxide is formed. So the part of that rock gets dissolved as bicarbonate ions, and that results in washing off of that rock from a particular place. Third is oxidation, where oxidation of some mineral takes place, particularly wherever iron is present. These yellow patches seen over this rock material is a result of oxidation of iron which is present here. And oxidation of iron minerals and rocks result in its loosening, it's a loose structure, it results in heaving. Heaving means upward movement which is loose in structure and it is easily washed. That also results in formation of microfractures, cracks, and results in foiling or abrasion of the upper layer very easily by different physical agents once the chemical material has been applied. Sinkholes are an example of uh, dissolution of calcium carbonate. These are generally observed in North America and Canada. The underlying geology is rich in calcium carbonate. As we said, as water dissolves CO2 to form H2CO3, the carbonic acid, and carbonic acid can dissolve carbonate of calcium carbonate in the form of bicarbonate and result in formation of large voids at such particular places. If the geology is such and if CO3 gets dissolved from the calcium carbonate mineral, sinkholes generally are observed. The land normally subsides in those cases. So that is an example of an amplified example of carbonation where calcium carbonate gets dissolved in water. Finally, the biological weathering, it is because of the microorganisms, the lichens, etc., and the vegetation. And growth of these microorganisms or vegetation is responsible for cracking of these rocks. It is the physical force for the vegetation, for the lichens and microorganisms. These are the biochemical reactions which take place since microbes secrete certain enzymes, and these enzymes are responsible for solubilization of even the mineral structure, mineral molecules. And that results in loosening of the uppermost layer of the rock and results in chemical. Once chemical weathering takes place, the soil is formed. This is the weathered rock, but in order to make soil complete, it also requires the organic matter, air, and water to be present in. So naturally, when soil has formed, the components of soil or its profile is classified as 4 different layers. Sometimes the layers are 5, and depending upon the extent to which we are studying the soil profile, there could be more number of layers because the soil scientists who are specifically working in the field of soil science, they have more number of layers, more classification of these layers of soil. So profile for as far as environmental geotechnology or environmental science is concerned, these 5 profile, 5 layers of soil define almost every part of it. So the components of soil are rock material, rather the weathered rock material, organic matter, air, and water. The organic matter is it comes from the plants and animals chiefly, plant and animal origin. The plants they shed their leaves and the dead and decomposing biomass forms major organic part, organic matter present on the soil, and it is mainly the topmost layer is present above the soil. So that dead and decomposing organic matter, the vegetative or animal in origin, which is present over the top of soil, is classified as the organic layer or O-layer. And this organic layer has a decomposing material organic material present in it. It has most of the nutrients which normally get recycled. It has microorganisms present in it, the unique matter present in it. And whatever gets mineralized, those soluble forms of minerals or nutrients keep leaching downward in the soil. Now, when organic matter has degraded and certain available nutrients have leached down to the soil, this forms the A surface. A surface is that layer of soil which contains the nutrients in abundance. And most of the nutrients remain confined in O and A layer, and therefore these two layers are very useful with respect to the agricultural practices. Most of the agricultural production depends upon these two layers because maximum availability of nutrients is present in these two layers. And this is also referred to as the topsoil. The soil to which the nutrients have not permeated down, and it is simply the soil and water present in it, is referred to as subsoil. Here the nutrients are not present, but water and air is present, and subsoil is similar to topsoil, excluding the organic matter and nutrients present. This is referred to as layer B. Layer C is the soil as well as some of the finer fragments of the rock out of which that soil has been formed. So substrate C is referred to as a mixture of the soil and the rock material, the weathered rock. And surface R is known as, layer R is known as the bedrock. Bedrock is the parent rock out of which the soil is forming. So this is how we classify profile of soil with respect to their size. And based on the particle size, the grain size, these can be classified as clay, silt, and sand. Sand can further be classified as fine sand and coarse sand. And there are further many classifications. Those who are studying soil science must be aware about it based on the predominant fraction of clay, silt, or sand present. These are classified as clay loam, sand loam, loamy sand, or silt loam, etc. Now we come to the soil contamination, which is a major part of this lecture. So once the basics about soil is known, let us specifically target the contamination of soil. There are few terms in soil contamination which are normally referred to in literature, information, or reports related to soil contamination. The first term is source. Source here refers to the place where the contaminant is originally concentrated. Source is the place, the physical location where the contaminant is present, is originally maximum in concentration. So that is referred to as source. The source can be placed on the surface of soil if it is, say, dumped at some particular place and it is present over the surface of soil, it's visible to us. That location is referred to as the source. But the source, if say rainfall takes place and this contaminant moves it down into the soil and there is nothing visible on the surface, then the source, it moves the subsurface. So source can be placed over the topsoil, over the surface, or it could be also be present subsurface. And this is the place, the physical location where maximum concentration of the pollutant is present. And the other term is source material. Source material is different from source in a way that it is the material which is having those toxic or hazardous properties. Over the surface, over the topsoil, if some waste is present, suppose it is fly ash, that would be referred to as source present at the surface. But this fly ash has inorganic impurities, particularly heavy metals present in it, and these heavy metals are the material which are resulting in imparting toxicity or hazardous nature to the soil. So here in this case, heavy metals or the fly ash would be classified as source material, and the source is the location where the contaminant is present. So there is a difference between the two. Source is the physical location of the contaminant, and source material is specifically that material, that pollutant which is resulting in toxicity or hazardous properties into it. Now, soil contamination, it can adversely affect the health of soil. At the same time, it also affects the health of those living on it. Health of the soil means the physical and chemical or biological properties of the soil are compromised. Suppose fly ash is disposed of on a particular part of soil, and this fly ash would be having very fine structure, very fine grain size. The grain size of fly ash is very small, and this would result in clogging of the pores of the soil wherever it is present. This results in decrease in porosity, decrease in permeability, decrease in hydraulic conductivity. Also, it results in increase in decrease in gaseous exchange. It may or may not, it may have an effect on the water holding capacity also. Since heavy metals are present in the same soil, these heavy metals are toxic in nature, and these may affect the microbial population present in soil. That way, the physical and chemical properties of soil might be affected, and that results in an adverse effect on the quality of soil. The other is the health of those living on it. The organisms which are living on such soil, the health of those organisms may also be affected. And these organisms could be plants, animals, microorganisms, or us, or human beings. There is a direct impact of soil quality on the health of plants which are grow over that particular place. Whatever sort of pollutants are present there, those pollutants can adversely affect the health of that plant, that vegetation. This broadly we can say that this results in stunted growth. The growth is less, production is less, and many times these pollutants keep accumulating in the plant tissue as well. Although the growth is stunted, at the same time these pollutants are getting accumulated, and the animals or the herbivores which feed on such vegetation will be getting an exposure to those pollutants through the food chain, and ultimately it reaches to the top carnivore or climax community in the food chain. In most of the cases, the climates community are human beings. So therefore, soil pollution, it does not specifically affect the quality of soil or health of soil. It also affects the health of organisms which are dependent on the soil. And this pollution of soil may be an outcome of an accident, or it may also be the carelessness. Very recently, we have witnessed the case of oil spill at Mauritius that can be referred to as an accident. And in these days, after proper investigation, the same accident is also referred to as a case of carelessness. Yes. Because the oil tanker was stuck over the coral reef a week before it started leaking, and the government of Mauritius might have taken some certain actions to take it out, to bring it out from the coral reef, to pull it out of the coral reef so that the oil would not have leaked, because it was struck for more than a week, and the action of waves, the strong winds resulted in constant ripping of the surface of the oil tanker and it leaked. So what I meant to say is the soil pollution can be an outcome of, can be a result of an accident, or it could also be carelessness. To make it more clear, it may also be referred to as accident in case of Bhopal gas tragedy. That accident took place in 1984. Tons of methyl isocyanate it leaked and resulted in pollution of the soil. And the soil is so contaminated that union carbide premises even now that the vegetation does not grow there. Most of the vegetation fails to grow there. And the same accident may also be referred to as case of carelessness. After investigation, it was found that many of the pollution control equipments during that accident were not working properly even before the accident, months before the accident, and the authorities were not giving proper care about the proper maintenance and repair of those equipments, which led to that accident. So that can be any, and pollution, it may also be a byproduct of the normal activities. Suppose we at home are cleaning, sweeping the houses, and the waste, whatever is produced during the sweeping, is thrown out, is dumped at some particular place, and that waste keeps accumulating in one of the corner of the street. Now, with time, the waste is going to decompose, and the decomposition of that waste is resulting in addition of some of the other toxic impurities, toxic properties to the soil. The normal biodegradable waste may not be responsible for addition of some toxic impurities. But suppose if the house sweepings also have plastic, generally there is a tendency that the waste which is swept early in the morning from the houses is put into a polythene, is tied, and it is then thrown away or given directly. But the polythene, when disintegrates with time, the microplastics are imparted into the soil, and these microplastics have proven a record of hazardous or adverse effect over the health of soil. So that way, it could also be byproduct of activities. Byproduct of activities here, the other example could be agriculture. Although agriculture is a beneficial practice, that is a beneficial profession that is being practiced, but intensive agriculture, where repeated or frequent tillage, cultivation, etc., is being done, the nutrients which are present in soil are regularly being taken up. At the same time, the frequent tilling and plowing is resulting in disintegration of soil particles into finer grains, finer particles, and this results in slow and gradual compaction of the soil. And that way, the soil quality is affected, and that may also be referred to as soil pollution. The pesticides which are used in agriculture or the fertilizers which are used in agriculture gradually, slowly percolating down into the soil and are resulting in pollution. So that is a byproduct of activities, such activities. So it need not necessarily be an accident or case of carelessness when soil pollution is considered. It can also be a slow and gradual process, which is a byproduct of different activities. And the mechanisms by which this contamination of soil is taking place is by three mechanisms. Firstly, it is rainfall. Secondly, it is human activities, and thirdly, the physical-chemical alterations in properties of soil. Most of the pollutants, most of the contaminants, uh, when these are discharged or disposed of, would be present over the surface of soil. These would be present over the surface. As long as it is present over the surface, it is visible to everybody. And once it is visible, it is easy to locate, easy to collect, easy to transport, and easy to treat. So initially, it starts from the surface of the soil, from the top soil. The contaminants are disposed of or discharged over the surface, and then they gradually start moving downward, moving subsurface. Once a contaminant has moved subsurface, it becomes difficult to locate it. It becomes difficult to collect it, to take it out, and it becomes difficult to treat it. And one of the reasons for this movement of contaminant or contamination from surface to subsurface is rainfall. And rainfall results in, say, leaching of these contaminants or movement of the contamination from surface to subsurface, and that may, in some cases, may result even to the ground. The human activities, dumping of waste, will not go into details of human activities or dumping of waste. There are a number of activities, and dumping this nature of waste which is being dumped outside may vary from toxic to non-toxic. The normal kitchen waste is non-toxic in nature, whereas the industrial waste will be toxic in nature. Even the normal agricultural waste may not be toxic, but the different agrochemicals used for the crops, those may be toxic in nature. So there are a number of human activities which are resulting in disposal or discharge of contamination over the soil. The physical-chemical alterations in soil are also responsible for, is also one of the mechanisms for contamination of soil. And we just now discussed the case of agriculture, where the changes in physical and chemical properties of soil are taking place. Biochemical properties of the soil are also affected when pesticides, etc., or other agrochemicals are applied. The microbial population present in the soil is also affected. The population goes down as well as its diversity goes down. And in those cases, the quality of soil gets poor and the soil gets contaminated. As long as the microorganisms are present in the soil, they have a tendency to break the contaminants or organic molecules down into simpler forms, convert them to available forms, and that way the soil quality is maintained. But if the microbial population is affected, if change in physical biochemical properties of soil takes place, in those cases, the rate of soil contamination gets accelerated. So these are briefly the three mechanisms, and these affects either the soil structure or geochemical properties, where the mineralogical and chemical characteristics of the soil are changed. This may also result in change in groundwater characteristics if the contaminant moves through the soil to the groundwater. And these soil-water interactions contaminant are responsible for transport of contaminant from one place to another. Now, contaminant transport takes place through these three different processes. The first one is advection, and advection takes place along the hydraulic gradient. Along the hydraulic gradient here means it moves along with the groundwater flow. The other is diffusion, and diffusion it is the movement of contaminant along the concentration gradient. There is a general tendency that a particular solute moves from region of higher concentration to region of lower concentration. So that is referred to as diffusion. And similar sort of diffusion is observed in soil also. The contaminant moves from the region of higher concentration to region of lower concentration. The region of higher concentration is the place where the source is located, and it keeps moving in all the directions around that source. So that is referred to as diffusion, and it takes place along concentration gradient. And third is dispersion. Dispersion takes place along the groundwater velocity. We shall be discussing these three in the coming slides. But dispersion, the rate of movement of a contaminant may vary from place to place. To some of the regions where the subsurface hydrogeological setting is such that the porosity or permeability is more, there the velocity of groundwater would also be more, and dispersion to that particular direction would be more. Against it, there could be some location where mostly clay and silt is present, the porosity and permeability is relatively less, and the groundwater velocity through such region would relatively be less, and dispersion in that direction would relatively be reduced. So dispersion is along the groundwater velocity, diffusion along the concentration gradient, and advection is through the hydraulic gradient. And these processes are responsible for movement of contaminant from one place to another, but this is for the non-reactive contaminants, the contaminants which do not react with the soil. On the other hand, the contaminants which can react, which can degrade, which can be degraded by microorganisms, for them chemical mass transfer and microbial degradation, both the factors are also considered. So this is an example of advection. Advection takes place along the hydraulic gradient, changing height of the groundwater table with distance, and it depends upon the effective velocity. To explain it to you, advection is the movement of contaminant along the movement of ground, and this advective flow results in the movement of contaminant in the direction of ground. This is a simple case of advection. I hope it is clear to everyone. In the other case, diffusion, it takes place from the region of higher concentration to the region of lower concentration. And this dc by dx represents the concentration gradient. D is the diffusive mass flux per unit time per unit area, and the negative sign is because the movement of contamination is taking place from higher concentration to lower concentration, and it is governed by or expressed by fixed the diffusion. Diffusion is like this. Suppose some contamination is present at a particular location, and this contaminant is concentrated here in subsurface region. Now, the region outside, the region away from this particular region, this doesn't have any concentration of this contaminant. This region does not have any concentration. This region does not have any concentration, and even this one. So the general tendency of diffusion is the movement of this contaminant would take place from the region of higher concentration to the region of lower concentration. And that way it is expected that this contaminant will be moving to this direction, this, and this direction. That way diffusion will take place. So this is how we say that movement of contaminant along the diffusion gradient is taking place. And this can be this way. The contaminant, the molecules move from region of higher concentration, which was initially here, to the region of lower concentration. As long as the concentration in this complete subsurface environment gets almost homogeneous, that depends upon the chemical equilibrium, that depends upon the conditions present in subsurface geology. That's how diffusion is taking place. And diffusion is different from advection in a way that if groundwater is moving from this left to the right direction, here in this case of groundwater flow is taking place from left to right direction, and therefore the movement of particular contaminant is also taking place from left to right. This is the region where the contaminant is concentrated, the blue region. The blue region is the contamination, and the, as far as advection is concerned, this contaminant would be moving to the right along with the groundwater flow, since groundwater flow is to the right side. Whereas in case of diffusion, here the concentration is maximum here, where the contaminant is placed, the source is placed. And opposite to the groundwater flow, the concentration is relatively less. In case of diffusion, this contaminant would be moving from region of higher concentration to region of lower concentration. So in case of diffusion, the movement of a contaminant takes place against the groundwater flow, against the direction of groundwater flow. So this is the difference between advection and diffusion. In case of diffusion, it would be moving to the direction reverse to the groundwater flow, so subsurface flow. So third is dispersion, and dispersion is the movement of mixing of contaminant in different directions. Because the hydrogeological setting, the type of the fraction of silt, soil or clay which is present in subsurface may not be uniform. At some particular place, some particular location, silt would be more in concentration. On the other hand, sand could be more in concentration. Now, since sand has got coarser particle size, coarser grain size, so the pores present between these particles are relatively bigger, relatively larger, and it is easy for the contaminant to get transported, to move through the larger pores. So groundwater velocity through the sand would be higher, and the movement of this contaminant through the sand would be more, whereas on the other hand, where silt is present, the movement would relatively be slow. So this is dependent upon the groundwater velocity. Wherever groundwater velocity is more, the dispersion would be more. Wherever the groundwater velocity is relatively less, the dispersion would be less. And this can be referred to as it is given here. Suppose at particular this particular location, this one, this path, if it is considered, suppose these pores have relatively narrow space here. So this contaminant which is here would be moving relatively slowly because the path is restricted, is narrow. On the other hand, if this path is broader, is wide, and the contaminant can move easily. So with the groundwater velocity through this path would also be more, and the movement of this contaminant along this direction would also be more. So the contaminant was initially present at this place, but its movement along the groundwater flow is to different distances depending upon the groundwater velocity. This movement of contaminant to different distances in a given time because of different groundwater velocities is referred to as the dispersion. So I hope this explains the difference between the advection, diffusion, and dispersion. Advection is along the hydraulic gradient, diffusion is along the concentration gradient, and dispersion is along the groundwater velocity. The particular direction where groundwater velocity is more, the movement of contaminant will also. That way, the contaminant keeps dispersing. And one important factor in movement of contaminant is retardation. Retardation can be explained as this. The contaminants move along with the groundwater flow. Now, these contaminants have got affinity with the soil particles, depending upon the charge, depending upon the chemical nature. And the contaminants keep binding to the soil particles. Some of the contaminants which gets bound to the soil particle remain there for longer period of time, and others keep moving up, moving with the groundwater velocity. So the movement of contaminant is always less than, relatively slower than the movement of groundwater. This is referred to as retardation, and retardation is calculated as just wait, sorry. Retardation is calculated as the concentration of a contaminant present in unit volume of aquifer to the concentration present dissolved in ground. If we consider the aquifer as a whole, aquifer means the concentration present in groundwater as well as in soil, and this is the concentration present in groundwater alone. So the concentration of a contaminant in aquifer would always be more than the concentration present in groundwater. And for this reason, retardation factor would always be less than 1. Its value would always be less than 1. It is close to 1 only in the case of chloride. And this is the reason that chloride is generally studied as, is considered as a tracer in case of groundwater contamination or subsurface contamination. Now, the major contaminants which could be present in the soil, those could be acidic contaminants. Some acids are produced. Acidic contaminants, I hope most of you must have heard about or read about the acid mine drainage, particularly in coal mines or where iron pyrite, etc., are concentrated, wherever sulfur is there. This sulfur under anaerobic conditions this results in the formation of sulfides, and these sulfides upon exposure to oxygen results in formation of sulfates. The sulfates react with water to form sulfurous acid or sulfuric acid. Such acidic contaminants, when are discharged, disposed over the soil, results in contamination, and those result in heaving. Heaving is the accumulation of salts over the soil, and this is an upward movement. These salts keep depositing and keep expanding, and this results in formation of slightly upward movement, sort of protrusion over the soil, and this is referred to as heaving. Acidic contaminants where are present result in decrease in pH of the soil, and the decrease in pH significantly affect the microorganisms present in soil. MO here refers to the microorganisms, and the decrease in diversity as well as number of microorganisms is an indicator of soil contamination, poor quality of soil. The acidic contaminants results in heaving, deposition of salts, etc., and this results in reduction in permeability, porosity, etc. So the physical, chemical, and biological properties are affected by these acidic contaminants, and it is mainly by process of heaving. Similar to this, the alkaline contaminants, these can also result in heaving, deposition of salt. These can result in decrease in number and diversity of microorganisms, and effect over the permeability, porosity, and other physical properties of the soil may be rendered because of these alkaline contaminants. And the alkaline contaminants are in this case mostly the salts of sodium and calcium. Now there is a difference between the contamination potential of monovalents and divalents. The monovalent ions, in case of alkaline contaminants like sodium and potassium, they result in more expansion of the minerals, more expansion of the clays in particular. Whereas divalent ions, with calcium, magnesium, etc., are present, they result in relatively less expansion. Now, if alkaline contaminants have monovalent cations like sodium and potassium, these bind with the clay particles and result in their expansion. The expansion results in clogging of the soil pores. In that way, reduction in permeability, porosity, gaseous exchange, etc., is observed. In that way, the soil becomes infertile. And whenever water in the form of precipitation comes over, this results in waterlogging, and such soils remain contaminated for a long period of time. Waterlogging results in solubilization of all the salts present in that soil. Once the season of precipitation is over, summers arrive, during that period, water would evaporate and all the salts would be concentrated over the surface of soil. That results in imparting salinity or alkalinity to such soil. And saline or alkaline soils are not very productive. That is referred to as a type of contamination. Now there could be inorganic contaminants. The inorganic contaminants could be non-toxic, as we took the case of sodium, potassium, calcium, and magnesium. These are inorganic in nature, and these do not pose much toxicity to the organisms present in soil. Whereas some other inorganic contaminants could be toxic, particularly the metals or the heavy metals. Now, heavy metals are those which have a density more than 5 grams per cubic centimeter. And these are toxic in nature. Four metals qualify as heavy metals. These are mercury, cadmium, lead, and chromium. And some of the metals have toxic properties similar to these four heavy metals, although their density is less than 5 grams per cubic centimeter. Those are also considered as heavy metals as far as their toxicity is concerned. But as far as density is concerned, four metals qualify as heavy metals. So these are inorganic contaminants or heavy metals or trace metals. These may also be referred to as trace metals like mercury, lead, copper, chromium, cadmium, etc. These are toxic in nature. So whenever such inorganic contaminants are present, they impart toxicity to soil. They kill the microorganisms. And as the microbial count decreases, the soil quality is affected. The recycling of nutrients in the soil also ceases when some toxic impurity enters. And since decomposition of organic matter is not taking place, recycling is not taking place, the nutrients present in soil are not regularly recycled, and that results in reduced fertility of soil. So wherever inorganic contaminants are present, the soil becomes infertile. Such contamination needs to be taken care of. The organic contaminants, similar to those inorganic, are toxic in nature. They impart toxicity. They can affect the permeability. Organic contaminants are generally, say, hydrocarbons, the oils, etc. These are referred to as organic contaminants. And oil can block the pores. It can decrease the porosity. It can decrease the permeability. This can also impart toxicity, which kills microorganisms, and such soil remain highly contaminated. And these organic contaminants mostly are not soluble in water. And those which are not soluble in water are referred to as non-aqueous phase liquids or NaPLs. Now, these non-aqueous phase liquids or NaPLs would be light in weight. Those which have lesser molecular weight would be lighter, and those which have high molecular weight would be denser. And based on their density, these are referred to as low density NaPLs and dense NaPLs, high density NaPLs. So these are referred to as LNaPLs and DNaPLs. The LNaPLs float over the surface of water, whereas DNaPLs sink into water. They move down. As we study the case of oil contamination in seas and oceans, some of the oil floats over the surface. That is referred to as low density NaPLs. The one which sinks, reaches to the sediments, is referred to as dense NaPLs, those dense non-aqueous phase liquids, and these are toxic. There could be other trace organics. One of the examples is pesticides, which are normally used in agriculture. The trace organics could also be the mixture of oils, PCBs, polychlorinated biphenyls, the microplastics, etc., etc. And most of these pollutants are toxic or carcinogenic in nature. There could be other contaminants also. These days, the emerging contaminants, particularly the pharmaceutically active compounds, the pharmaceutical drugs which are being disposed of. Many times, the wastewater generated from pharmaceutical industries might be having a residual concentration of those antibiotics or anti-inflammatory drugs present in it. And if the same wastewater is, say, suppose, is discharged over the land, the water evaporates or moves down, and the drugs, be it antibiotics or some other drug, remain in the soil, and they have different effects on the physical, chemical, and biological properties of the soil. That way, this is a broad classification of different contaminants which could be present in soil. Soil trace organics, they result in decrease in microbial population, reduce as a result of decreased microbial population, there would be reduced aggregation of soil particles. The finer particles come together and bind, they aggregate into larger particles. So that is referred to as aggregation. In case the microbial population decrease, the aggregation of particles is generally not observed. This results in reduced porosity, reduced water holding capacity, reduced permeability, reduced hydraulic conductivity, the increased interlayer swelling, the different layers of soil which are overlying each other have a tendency to generally to swell, and that results in blocking of pores, and there would be reduced void ratio size. Now that we come to the treatment of contaminated soils, how do we treat it and what is the course of treatment? What is the objective of treatment? The objective of treatment of contaminated soil is to extract the pollutant or to immobilize the pollutant or to detoxify the pollutant. Whatever sort of pollutant is present, our strategy is either to take it down, bring it out, extract it, or to immobilize it. We do some sort of treatment by which the contaminant is not able to move from one place to another in the soil. Or we detoxify it, we degrade it using different physical, chemical, or biological methods. So there are different physical, chemical, electrical also, thermal and biological methods which can be employed for the treatment of contaminated soil. And this treatment for extraction, immobilization, or detoxification can be employed either at the place of contamination. If it is employed at the place of contamination, it is called in situ treatment. But if the soil from the contaminated place is taken out and is transported to some other place and treated there, that would be referred to as ex situ treatment. So in situ mainly containment is done, but ex situ generally the remediation is done. The in situ treatment is relatively less expensive. On-site treatment is relatively less expensive. It results in lesser exposure and it results in minimum disturbance to soil. But it has certain challenges also, the in situ treatment. Whereas on the other hand, ex situ treatment, off-site treatment is expensive. It results in exposure. It has constraints with respect to the site, the conditions present there. Space is required for ex situ treatment because the machinery, the infrastructure, etc., which is installed for the treatment of such soils requires a certain space for their installation. Transportation of such contaminated soil from one place to another is required. And of course, there are regulatory law-related aspects which need to be taken while devising a strategy for treatment. So in case of in situ treatment, for the on-site treatment, we generally devise a strategy to prevent the spreading of contaminant. We generally try to restrict the movement of contaminant from one place to another to reduce its health hazard. And this can be a permanent remedial action. This can be a permanent treatment in some cases. It may not be a permanent treatment in all the cases. The containment is generally done to allow authorities with the time. The authorities or the task force gets some time to devise the strategy and then treat or take the pollutant out once containment is done. So it is about delaying the movement, delaying the effect of it in subsurface. There are two types of containment methods. One is passive system, the other is active system, the passive method or active system. In case of passive containment systems, the vertical barriers are employed. This is the waste present at a particular location in subsurface environment. Now, in order to avoid its movement from one place to another, what we do is we install vertical barriers, and these barriers are impervious in nature. These barriers do not allow movement of this contaminant from one place to another. Now, once the movement of this waste is restricted, we have sufficient time to devise our strategy to treat it. एक बार हमने इसको रेस्ट्रिक्ट कर दिया, फिर हमें समय मिल गया है, उसके बाद we can devise the strategy and we can either take it out, extract it, take it, transport it to some other place and can treat it. दूसरा, if we are very sure that there is no other external force which is resulting in movement of this waste, once this barrier is installed, this place remains isolated. And this place, if it is isolated, if it is not used in future, can be left as such because the waste would remain there itself. And some of the wastes have a property to attenuate, to degrade with time, such as the organic waste. So once isolated, this waste remains as such, and with time it may detoxify under natural conditions. So in that case, it could be a long-term solution. But if there is a possibility that this waste can reach, can with time, can cross these vertical barriers, in that case, we have relatively lesser time. The waste is to be extracted, the waste is to be treated in this case. So employing these vertical barriers allows us some time to react, to respond towards treatment of the waste. So this is one of the passive containment method where vertical barriers are installed. And these vertical barriers could be vertical cutoff walls or barrier walls. These are also known as the vertical cutoff walls, cutoff barriers, or barrier walls. And there are different configurations how these walls, these vertical barriers can be installed. These can be from the top to the bottom barrier. Somewhere, suppose the waste is placed and the bottom is impervious. So one vertical barrier. We will have some discussion in the coming slides. These can also be the hanging one. These can be placed over the aqueduct. And for low density non-aqueous phase liquids, these could be hanging over type of vertical barriers. So this is one type of keyed in slurry barrier, where the underlying layer, this is an aquitard or the impervious layer, and the contaminant will not move down to this layer. The flow is towards this direction. The movement of contaminant is from left to right here. Suppose the movement of contamination is from the left to right. A slurry wall would be placed here. This slurry wall is made of clay, normally bentonite or marillonite or normal clay can be used. It is dug up, a hole is laid, a trench is made, and we fill it with the slurry of the clay. And since clay is impervious, the contaminant or the waste would be moving up to this slurry wall and would be arrested here. This slurry wall will not allow further movement. And down here, there is an impervious layer. So here in this case, the waste remains almost isolated in nature. And this will not allow the movement of this waste from one place to another, and this will not allow the harmful effects of this waste on other components of environment. That is how the vertical barriers can be placed. This could also be hanging slurry barriers, where this the impervious layer is placed below. There is a gap between the vertical wall and the impervious water. There is a gap. But here in this case, the water table is placed here. This water table results in movement of contaminant along with the hydromic gradient. So the contaminant, wherever it is being discharged, would be moving down, and this would be moving with the flow of water advection. Now, what we do is we install a slurry wall which is hanging in nature. But this hanging slurry wall should go deep down below the groundwater table. The groundwater table is placed here. The slurry wall should go deep down the groundwater table, say 1 or 2 or 3 meters below the ground. Now, whatever contaminant is coming down, it will be moving along with the groundwater flow to this direction. And immediately before the slurry wall, we place an extraction wall. In this extraction wall this extraction well would be pumping or extracting the groundwater out. And along with the groundwater, the pollutant would also be extracted out. So once the contamination from here is sealed through the extraction wall, with the help of this extraction well, and with the help of this slurry wall, the pollutant can be extracted out before it moves to some other place downstream, down the grid. So that way, we can arrest the movement of this contaminant from one place to another. And in this case, this extraction well is an active system. The slurry wall is a passive system which contains the pollutant, but the extraction well is the active system which takes the contaminant out and treats it. So the configuration or the placing of these vertical barriers may also be called horizontal configuration if it surrounds the waste this way. The waste is placed here. In this case, this is the waste, and we do not know how would be the movement of this waste. In that case, the waste can be contained all around. Once the waste is contained all around, making a slurry wall, the groundwater flow will be taking place around this slurry wall. This will not allow the lateral movement, that's straight movement of water and the interface of with the waste. This will not be allowed. Rather, the water would be moving around this slurry wall, around this barrier, and it goes out. That way, the waste doesn't have an interface with the water, and this contamination is not carried down greatly. So this is one of the way the circumferential barrier which can be placed depending upon the configuration that we are discussing. So this circumferential barriers isolate the waste all around it. Now, the barrier could also be placed up gradient or down gradient. These are two other configurations. In the earlier case, we provided a barrier all around the waste, and in these cases, we are either providing it up gradient or we are providing it down gradient. So these are different configurations for the containment systems. Here in this case, a slurry wall is placed up gradient of the waste, upstream of the waste. The groundwater is flowing from this direction to this one. Now the groundwater, instead of flowing straight, will be moving along these lines. The groundwater moves along this direction, and the interface with the waste is arrested. It does not react with the waste, and therefore this waste will not be moving to this direction. The movement of this waste will not be observed. That way we can avoid the interface of groundwater with the waste. The waste will remain there, and we get some time to either take it out, to treat it, or to naturally attenuate it, to naturally get it. This is one of the configurations, the up gradient barrier. The other is down gradient barrier. In this case, we allow the waste to react with, to interface with the groundwater. The groundwater flow is taking place in this direction. Groundwater reacts with the waste. The waste, the soluble impurities, soluble contaminants get dissolved in water and would be carried downstream of this source. This is the source where the waste is placed. So this would be the place. And a downstream barrier is placed. This is the downstream. This one. A downstream barrier is placed. This barrier does not allow the groundwater flow. And immediately here, certain extraction wells are placed just before the barrier. Extraction wells are placed. These extraction wells would pump the water out along with the contaminant, and this pumped out water would be treated. That way, the subsurface soil contamination can be treated. The extraction well in this case would be an active system, and this slurry wall provided here, this would be a passive system for the containment of the. So depending upon the configuration, this could be circumferential, this could be up gradient, this could be down. Now this vertical barriers could be made up of soil bed. These could be compacted clay barriers. These could be slurry trench barriers or grouted barriers, mixed in place barriers or steel sheet pipe barriers, depending upon the properties, depending upon the availability of material, properties of the content. And normally the compacted clay or slurry trench barriers are used to arrest the movement. These are made up of mixture of soil along with bentonite, cement bentonite, plastic concrete, or composite barriers. These could be different materials which are mixed together, and an impervious barrier is placed. These could be grouted barriers also, where jet grouting or permeation grouting or vibrating beam method can be employed to inject this slurry material into the barrier. So depending upon these types, these could be different types. In case of active containment system, we said we have pumping wells or subsurface drains. Normally the pumping wells are used. But if there is a drain nearby, and if groundwater is moving subsurface to that drain, in that case, a subsurface drain may also be used to carry the to transport the contaminant from one place to another, because the subsurface drain is finally coming out over the surface in another drain. So there the waste can be collected and waste can be treated. This is how the active systems are working. The waste gets an interface with the groundwater, and this through the extraction wells it is taken out and then it is treated. The domestic well, which is used for day-to-day activities, for drinking, etc., these extraction wells should always be placed up gradient before the domestic wells. So that's how the active systems are working. Now the common technologies which are for soil remediation. Now earlier to this we were discussing about the containment methods, and here we shall be discussing the soil remediation methods, in particular the soil treatment methods. And the soil treatment methods would be excavation and disposal. This could be soil vapor extraction, thermal desorption, vitrification, soil washing, stabilization and solidification, electrokinetic remediation, and finally bioremediation. So these are different approaches, different methods which can be employed for remediation of contaminated soil. We shall be discussing those one by one. So first of all, we go to excavation and disposal. This excavation and disposal is also known as dig and haul system. Suppose the soil at particular place gets contaminated. What we do is, it's a layman's practice, that contaminated soil is taken out and it is filled at some other place where the underlying layer is impervious in nature. So that this contamination which was present here does not move down. So the normal practice is take the contaminated soil out and fill it at some other place where it is contained, where the contamination does not move from one place to another. But it is a limitation here. Heavy machinery is required depending upon the scale of contamination, and this contaminated soil is to be refilled at some other place, and this dug out place should be filled with fresh soil which is to be transported from somewhere else. So there are issues related to operation, but otherwise technically with respect to toxicity, etc., this is relatively an easy approach to follow. Excavation and disposal or dig and haul system. But if the contamination is over a large space, अगर contamination बड़े area में हुआ है, in that case it becomes difficult, sometimes it becomes impossible to take a large area of soil, to dig a large area of soil and transport it to some other place and fill it there and fill the dugout space with the fresh soil. So there are issues, but it is relatively easy to operate. So that way, dig and haul system, it's an easy approach. Take the contaminated soil out and fill it at some other place where it remains contained. The other approach is soil vapor extraction, and I want to make it clear here that soil vapor extraction can be employed only in case of volatile organic contaminants. The contaminants which are volatile in nature and where the soil is sandy or the soil is permeable. It can be employed only at such places. Here in this case, what we do is, suppose some contamination has taken place subsurface. So this is where the source material, the contaminant is placed. What we do is dig a well here and we apply vacuum with the help of a vacuum pump. The air around this place would be sucked in and a vacuum would be generated. Now, once the air present in soil is sucked out, the empty pores would be filled by the vapors of the contaminant. And since the contaminant is volatile in nature, these contaminants would gradually be moving along with this air, and these would be taken out. Now, the stream of air which comes out, that can be condensed, that can be treated. That's how soil vapor extraction works. But it can be employed only in case the soil is homogeneous, highly permeable, mostly sandy in nature, and the contaminant is volatile in nature. So only in that case, this soil vapor extraction can be employed. And this is relatively easy to operate. There are not much issues, technological challenges involved in soil vapor extraction. Third is thermal desorption. Many times the contaminants are volatile in nature, but these also have an affinity for the soil. And these get bound to the soil. These get absorbed over the surface of soil. Once it is absorbed, they won't move that easily, but the contamination remains in soil. How can we remove such contaminants is with the help of thermal desorption. Here what we are doing is we are employing high temperature. Temperature of the order of 200 to 1000 degree Fahrenheit is employed, and this increase in temperature of the soil results in desorption of the volatile impurities, and these once these are dissolved using an extraction well, employing the vacuum, these impurities can be pumped out and these can be treated over the surface. So that's an easy approach for thermal desorption. Now, the beauty with thermal desorption is that it can be employed either in situ, where contamination has taken place, and this can also be employed ex situ. If the machinery, etc., which is to be employed is large in size, in that case, the soil from here, the contaminated soil, if it is near to the surface, that can be dug out, can be moved to the treatment facility, and there, thermal desorption of such soil can be employed. And once the soil is treated, this can be brought back and filled in the place from where it was dug out. So this can be applicable for oil refining waste, for coal tar waste, for wood treating waste, for creosote, for hydrocarbons, mostly volatile in nature. And these are the different pollutants, either chlorinated solvents, fuels, PCBs, mixed waste, pesticides, paint waste, synthetic rubber, processing waste, etc. But there are few disadvantages associated with thermal desorption. And those disadvantages are dewatering may be necessary to achieve acceptable soil moisture level before thermal desorption is applied. So initially, the water or the moisture present in the soil is to be removed. So sometimes in situ treatment gets difficult if moisture content or water content in the soil is more. In that case, the soil is dug out, it is dried, and then it is thermally desorbed at an ex situ location, and then it is brought back. So there are specific particle size and material handling requirements. The particle size should be relatively larger. The clay and silt relatively have more binding affinity with these pollutants, and therefore the removal using thermal desorption in case of silt and clay would relatively be less, and the reaction time in these silts and clays would be more. So that's how it's ineffective in treating inorganic contaminants. The heavy metals, etc., will not be treated because heavy metals, though they get thermally dissolved, these are not volatile in nature, they remain in the soil. And these cannot be taken. So this can be employed only for volatile pollutants. The next is vitrification, and vitrification is treatment of soil at very high temperature to a temperature that soil melts. And it involves the use of heat to melt and convert the contaminated soil into stable glass or crystalline product. In this case, what we do is certain graphite rods are inserted at the temperature of the soil where a contaminant is located. Suppose the contaminant is located here. Certain graphite rods are inserted into the ground, and these are heated. Temperature of the order of 1400 to 1600 degrees Celsius is reached. Many a times the temperature required, depending upon the properties of soil, could be high, and it is heated to a level that this soil where contaminant is placed gets molten in steel. It melts. Once it melts, the contaminant also enter into the molten soil, and then when it is allowed to cool, this takes the shape of almost a glass. You must have seen the vitrified tiles. Vitrified tiles have undergone similar sort of treatment. So that way vitrification is done, and the contaminant which was present in the soil gets immobilized, gets fixed in this glass. Neither this glass nor this contaminant is going to move from one place to another. But the limitation is that such soil cannot be used now. Once it is converted to glass, a solid mass, this cannot be used for other activities. A building cannot be erected here. But if it is very deep, in that case, this soil can be, overlying soils can be used. But otherwise, this soil has become glass now. This has absolutely no use. Now, vitrification, similar to thermal desorption, can be done in situ. This can also be done excessive. This soil can be taken out, converted to glass. The contaminated soil can be used in manufacturing of tiles, etc., or some other products. And in that case, the contaminant gets fixed, gets vitrified, and at the same time, we are getting it in the form of some product, in the form of some tile, etc. So ex situ vitrification is generally preferred, in situ is avoided. But if there is no possibility of ex situ vitrification, in that case, in situ vitrification would be done. And this is normally done for the inorganic contaminants, particularly the heavy metals. These heavy metals keep immobilized in the glass, in the vitrified side. So it is applied generally for the radionuclides and metals. The radioactive impurities can also be immobilized using vitrification. That's how we do it. Now next is soil washing. And this soil washing is an accident. If you recall the first sort of treatment, dig and haul system. In that case, what we did is we took the contaminated soil out and we filled it at some other place. Instead, what we can do is we can take the contaminated soil out, we can wash it using a particular solvent. Now, this solvent, which particular solvent would be used, it depends upon the properties of contaminant. If the contaminant is water soluble, plain water can be used. If the contaminant has got better solubility under acidic conditions of water, under low pH of water, in that case, acidified water can be used or alkaline water can be used depending upon the properties. But if the contaminant is organic in nature, in that case, an organic solvent may also be required. So that way, the contaminant can be taken out, it can further be treated, and the treated soil can be brought back and can be filled from where it was cut out. So soil washing is relatively easy. It can easily be practiced, but certain machinery is required. The cost is involved in soil washing. But the good thing about soil washing is the soil is taken out, it is treated, and it is filled back at the same place. And gradually, such washed soil, gradually, slowly, it attains the properties of natural soil. Once certain nutrients, certain microorganisms are added to it, it reaches to the level of its natural background conditions. So that's how soil washing can be done. But there are certain disadvantages also. Large volumes of solvent are required. And suppose the contaminant is organic in nature, in that case an organic solvent is required. The organic solvents evaporate very easily, and in that case exposure to the contaminant as well as exposure to the solvent to the personnel involved in handling takes place. And large space is required, of course, for the washing of soil. So this is another method for soil treatment. For this stabilization and solidification, immediately before this soil washing, we had discussed about the vitrification. So vitrification is also an example of stabilization and solidification. This can also be done with the help of certain additives, certain binders. And a very simple binder is cement, very simple binder is clay. The clay or the cement can bind with certain contaminants and can render them immobile or less soluble, or, although these remain toxic. But once the contaminant doesn't move from one place to another, it gets stable, it gets solidified. In that case, the toxicity is removed. Toxicity remains there, but exposure to the toxicity is removed. And stabilization and solidification can be done either in situ or ex situ. Advantage is that it is low cost and it is applicable to wide variety of contaminants. It can be applied to different types of soils, and it has got high efficiency towards treatment. But it has certain disadvantages at the same time. The contaminants in case of solidification and stabilization are not destroyed. These are simply immobilized. The volume of soil which is treated, addition of additive is increased. Initially, it could be 1 ton of soil, and to 1 ton of soil, suppose 200 kilograms of some additive is added. Finally, it becomes 1.2 tons of soil. So the soil increases in volume. Here, in this case of stabilization and solidification, VOCs, particulates, emission of VOCs and particulates may take place during the mixing process, because during the solidification process, certain additives which are used are volatile in nature, and those volatile impurities may result in exposure of the personal. And in this case, long-term efficiency of this process is uncertain. Once it is immobilized, it is solidified using cement, but cement, this immobilized mass has a certain life. After 50 years or after 100 years, this contaminant may start solubilizing, resolubilizing into water again. And in that case, this is treated as the disadvantage of this process. Next is bioremediation. Bioremediation is with the use of certain organisms or plants or some living organisms. But first and foremost in it is phytoremediation. So phytoremediation here, it refers to the treatment of a contaminant using plants or vegetation. And these plants or vegetation, there is specific criteria for the selection. These should be indigenous. These should grow in the conditions where the contaminant is present. These should be resistant to environmental stresses, because wherever environmental contaminant, soil contaminant is present, that is going to exert a stress over the plant also. So these plants should be resistant to stress. These should be hyperaccumulators, should accumulate the contaminant to a high concentration, and these should be perennial in nature. These should grow in all the seasons. We cannot choose the plants which grow only in the summer season. And whatever contamination is taking place or whatever treatment is to be required during winters or other seasons cannot be compromised. So these are the properties of vegetation which is ideally suitable for phytoremediation. There are different processes during phytoremediation. The first one is phytoextraction. In this case, during phytoextraction, the contaminants which are present in the soil are extracted. These are soluble in water. When water is taken up by the plants, along with the water, the contaminant is also taken. And these contaminants are finally stored in the leaves and other tissues of the plant. This process is known as phytoextraction. The other is phytostabilization. In this case, what happens is the roots secrete certain enzymes, and these enzymes are responsible for aggregation of soil particles. The smaller green size of particles, they come together and aggregate into larger particles, and with the help of these enzymes, these aggregates, these immobilize certain pollutants. And that is referred to as phytostabilization. But phytostabilization is temporary in nature. Once the plants are removed, these would get unstable again because the environmental conditions will change. The other example of phytostabilization is that these impurities are taken up, and these enzymes or proteins present in the plants, these bind with the impurities, particularly the heavy metals. The heavy metals get bound to the proteins present in leguminous plants. And these proteins are known as metal binding proteins, MBPs. And once the metal gets bound to this protein, it becomes immobile in nature, it becomes stable in nature. So such process is referred to as phytostabilization. Now the enzymes, etc., which are secreted by these roots, these are responsible for degradation of certain organic contaminants, the oils, hydrocarbons, etc. So enzymes can degrade these organic contaminants, can break it down into simpler forms, into available nutrients, and these available nutrients can then be taken up by the plants. And this is referred to as phytodegradation, and the other is phytostimulation. What happens is the leaves of the vegetation are responsible for photosynthesis. And during photosynthesis, whatever food, whatever oxygen, etc., are produced, these are transported to other parts of the plants as well. So when oxygen finally reaches to the roots, some of this oxygen is released to the neighboring soil into the rhizosphere, and this results in oxidizing formation of oxidizing conditions in the soil. And this oxygen may be responsible for enhanced degradation of these organic impurities, which were phytodegraded. So this enhanced degradation of organic contaminants by addition of oxygen to soil is referred to as phytostimulation. And we shall be having a discussion about phytostimulation in the coming slides also. That way, phytostimulation and phytodegradation work simultaneously, and that way organic contaminants are degraded. Some of the contaminants are taken up as such, certain organic contaminants, these reach to the leaf, and from the leaves, upon exposure to the sunlight, these are transpired, these are evaporated into the atmosphere. So that process is referred to as phytovolatilization. So there are different processes which are taking place in phytoremediation, and all these processes keep on taking place simultaneously. Therefore, plants are taking care of treating the inorganic contaminants as well as the organic contaminants. So this is the beauty with this phytoremediation. And phytoremediation, it is an in situ technique. It can be employed at the place of contamination. There is no machinery required, no cost required. Only cost required is putting the vegetation at the contaminated site. So therefore, this is a cheap alternative compared to the other physical and chemical treatment methods. And there are different processes which are operating in phytoremediation. There are certain plants which are suitable for phytoremediation, and we shall be discussing those which are suitable for the treatment of soil only. Most of the brassica species, the mustard species plants are good for treatment of contaminated soil. The leguminous plants, the pulses, lentils, etc., those are good hyperaccumulators. They can treat the soil easily. Tobacco is one good hyperaccumulator, one good phytoremediating agent. Sunflower is also one such agent. There are other plants also, but these are the major ones which are responsible for treatment of contaminated soil. The microbial remediation in bioremediation is also an important aspect. Microorganisms also secrete certain enzymes, and these enzymes are responsible for detoxification, degradation of these contaminants to either the less toxic compounds or into water and carbon dioxide. And this is a natural process. Therefore, this approach is eco-friendly and sustainable using microorganisms. This is an example where cypermethrin is a pesticide. It is a toxic impurity. The microorganisms would be acting upon cypermethrin, would be breaking it down into 3-phenoxybenzoic acid. This would again be acted upon the enzyme secreted. This would finally be broken down into inorganic matter, and this inorganic matter is the available form. That's how the microorganisms are playing a role in soil decontamination. But bioremediation, phytoremediation, or microbial remediation is relatively a slow process compared to the physical and chemical. So there is an important term for bioaugmentation. Bioaugmentation is the addition of microorganisms. Suppose at a particular place, certain contaminant gets introduced into the soil and the microorganisms present at the place are killed. In that case, certain resistant microorganisms from some other place can be introduced to the contaminated soil. And these resistant microorganisms, with time, degrade the impurities, degrade the contaminant into simpler forms. This approach of introducing foreign microorganisms or the organisms from some other place to the contaminated site is referred to as bioaugmentation. So bioaugmentation is a way to expedite, to increase the rate of degradation of organic impurities. It is to expedite the rate of treatment, the time required for treatment. The third is biostimulation. We just had a discussion about biostimulation in phytoremediation, wherein certain nutrients are added to the soil to increase the activity of microorganisms. And this addition of nutrients could be in the form of nitrogen, phosphorus, carbon, or organic biostimulants or oxygen. Once these nutrients are abundantly present in soil, the activity of microorganisms would also be more. And better the activity of microorganisms, better would be their degradation potential. And faster would be the rate of treatment of such soils. And since these nutrients are building blocks of life, they help in biochemical process of microorganisms. This process is referred to as biostimulation. Next is bioventing. In this case, oxygen is supplied to the soil at high pressure, and this oxygen provides oxidizing environment to the microorganisms present there. At the same time, the air, when it comes out through the soil pores, it also takes a certain volatile impurities out. So that's how bioventing is done. So bioventing is expediting the role of microorganisms in venting organic contaminants out. Sometimes the organic contaminants are not easily volatile. These are bound to the soil particles. So when microorganisms, their activity is improved because of oxidizing environment, the enzymes secreted break the organic contaminant down into relatively simpler forms which are volatile in nature, and these simpler forms are vented out. That's how bioventing is done. One of the other important process in bioremediation is land farming. In this case, the contaminated soil is taken out and it is spread over a prepared bed. It is taken out to some other place, it is spread there. The microbes are spread over the same contaminated soil. Nutrients are provided, and the rate of degradation in this case is relatively faster compared to the native soil, compared to the in situ conditions. So land farming is taking the contaminated soil out and treating it at optimized conditions, optimized with respect to the microbial growth and with respect to the environmental conditions. Once such soil gets treated at a land farm, this can be taken to the place where it was dug out and this can be refilled. Composting is also one of the examples, but composting can be employed only for easily biodegradable organic components, and this is again the role of microorganisms. Now, finally, if we carry out the strength, weakness, opportunities, and threat, the SWOT analysis of these physical methods, we find that uh, solvent extraction and electrokinetic treatment. We haven't discussed electrokinetic treatment, but this is with the application of electric current inside. So when electric current, electric potential is provided, one of the electrode is cathode, other is anode. Anode has positive charge, so all the negative ions would be collected over the anode, all the positively charged ions would be collected over the anode. The electrodes can be taken out and can be cleaned. So in case of physical methods, we find that finally the cost is moderate in case of electrokinetic treatment and solvent extraction or wash, whereas thermal desorption or microwave heating or vitrification are relatively costly, and there are certain weaknesses associated with these. So we will not be going with all the details of this SWOT analysis since the time is limited. I'll be sharing this request to Mohsin to share these slides with all the participants. I'll share a copy of it and you can go through the SWOT analysis of physical methods. Similarly, the SWOT analysis of chemical methods is given. Here, the cost of treatment in case of chemical methods is always high. Although its treatment efficiency is good, this can treat the contaminants, be it inorganic or organic in nature, and the weakness is large amount of solvents, large amount of chemical is required, the cost increases, but the strength is that the treatment efficiency of chemical methods is good. In case of biological methods, the cost is always low to moderate, and these are most preferred. Only weakness with the biological methods is that their rate of treatment is slow. They treat the contaminants at relatively slower rate. So finally, concluding this lecture, we would say that initially the contamination of soil should be avoided. So first and foremost practice is to avoid decontamination. Do not allow the contaminant to come in contact with the soil. Once it has come into contact, restrict the disposal and discharge. So we will have to restrict the amount which is being disposed of, which is being discharged. And restriction can be done by recovery and recycling. Once the soil gets contaminated, that soil can be treated immediately, because if it is not treated, if it is not contained immediately, the contamination is going to spread. And treating larger volumes of soil is a bigger challenge. And we can use a combination of different techniques. These could be a combination of containment, treatment, physical, chemical, biological methods for treating the contaminated soil. And finally, even if the soil has got contaminated, we will have to adopt certain mitigating measures by which the soil can be eco-restored, can be restored to its natural state. So with this, we conclude this lecture on soil remediation. Thank you very much. These are my contacts, and we'll be happy to share the doubts if anybody has got.
Thank you, sir. Audience, any questions, please?
Hello, sir. Do you hear me, sir?
Yeah, I can hear you.
Yeah. Good morning, sir. I am Mitandas from West Bengal, sir. I have few doubts. The first one
Yes.
is, what is the purpose of slurry wall in case of hanging slurry condition?
Can you repeat your question?
One of the question is, what is the purpose of slurry wall in hanging slurry condition?
Okay, the purpose of slurry wall is to avoid, to restrict the movement of contaminant. Once a slurry wall is erected, it will not allow the movement of contaminant down gradient. And up gradient, if we install an extraction wall, that would be taking the contaminant out and would be treating. So this hanging slurry wall is employed only in case the groundwater table is above the aquitard, above the impervious layer. And this hanging slurry layer should reach down below the groundwater. So this is to restrict the movement of contaminants.
Anyone else?
Yes, sir. Okay, sir. Sir, again, another question is, sir, I do not
Yes.
understand that at vection, you have told that at advection after this diffusion understand, but advection is not understand, sir.
Advection is simply the movement of a contaminant along with the groundwater flow. जिस भी डायरेक्शन में ग्राउंड वाटर की स्ट्रीम जाएगी उसी डायरेक्शन में कंटेमिनेंट उसके साथ चला जाएगा. दिस इज सिंपल. Suppose suppose this is not similar. Suppose you consider soil as a contaminant in this case, surface, and if rainfall takes place, the surface runoff takes soil along with it as suspended in impurity. This movement of soil along with this surface runoff is similar to the advection which is taking place subsurface. This is movement of contaminant along with the groundwater flow.
So
Okay,
participants,
sir. Clear, sir. Sir, kindly zoom in the in situ vitrification and soil washing diagram.
Okay, I'll have to go back to the screen. Just a minute, wait a moment. Yes, can you see the screen now? Can you see the screen now?
Yes, sir. I have seen, but sir, kindly tell again the mechanism, sir, in this in situ vitrification.
In case of in situ vitrification, what we do is we insert the graphite rods and we increase the temperature of contaminated soil. We increase the temperature of contaminated soil to a level that it gets molten in state. The soil melts. And once the soil has melted, we take the rods out and this soil gradually solidifies. And this solidifies as a glass. So this remains solidified. The contaminant, whatever was present here, is converted to glass, and glass is inert in nature, it doesn't react. So that way we solidify it.
Sir, and again, sir, soil washing mechanism, sir. I just
In case of soil washing, okay, in case of soil washing, the soil is taken out and it is washed using a suitable solvent. And once it is washed, it is then refilled at the place from where it was excavated. Now, the properties of solvents vary with respect to the contaminant. Whatever sort of contaminant is there, suitable solvent would be selected.
okay, sir. All doubts are clear, sir. Thank you, sir.
participants, anyone else? If you want to ask some question. So, sir, I think we must
Thank you, sir.
conclude now.
Okay, Sinji, I'll share you a PDF of this presentation. And you
Okay,
can
sir,
share
fine.
it with it.
I
And
will share it with you.
for all of you, I would like to acknowledge uh, the role of Professor Krishna Reddy. He works in department. He works for environmental geotechnology in University of Illinois, Chicago. I had a chance to interact with him, to learn a lot about environmental geotechnology from him, and I have used a fair material as he provided to me during the course also. So I acknowledge his help and his permission to use these slides and whatever I have learned from environmental geotechnology from him.
Thank you, sir. Thanks a lot. So, on this occasion, I once again thank Dr. Haritash, as he has explained very beautifully us from the start of formation of soil, that how the soils are formed, whole process of weathering, how the weathering affects the soil phenomena, that chemical weathering as well as mechanical weathering, and then the different agencies like hydrolysis, dissolution, carbonation, all these affect the weathering phenomena. And then sir has also explained us the classification of soil, and how these soils are contaminated due to our own activities, our human activities, and then acid rains and some other physical as well as chemical processes, and how the structure of soil is affected due to contamination, and also the groundwater characteristics are affected, then the various technologies used for soil remediations. So all this has been explained very beautifully from the beginning of formation of soil to the contamination of soil. So I once again thank Dr. Haritash for being with us and giving us such a beautiful lecture. So once again I thank Dr. Haritash, and hope that we will see you soon other some other day in
Yes,
the some
sure, sure.
next coming programs. So thank you, sir. So thanks a lot.
Thanks to you. Thank you
Thanks,
very
sir.
much. Thanks to all the participants also.
Thank you, sir. Thank you. So participants, so now this session is over, and we will again be starting our next session at 11:30. So once I will have to leave this meeting, so I will switch off the meeting, and you please join within 2 minutes, as otherwise the recording gets affected. If we continuously go within one meeting, then the recording is done in only one session. All the recordings are occupied there. So I will have to leave this session. You can join within 2 minutes again. Thank you, participants. See you at 11:30.